problem number 14, it says the pH of a 0.001 molar hydrazine solution is 9.7. Determine the ionization constant Kb and the corresponding pKb. So the reaction can be written as NH2 plus H2O, this is aqueous and this is liquid. So NH2 NH3 plus aqueous plus OH minus aqueous. Now Kb will be concentration of NH2 NH3 plus times concentration of OH minus by concentration of NH2 NH2. So Kb is the ionization constant. The ionization constant of hydrogen. This is the value of Kb. Now given pH is 9.7, right? pH is 9.7, so therefore minus log of 10 base concentration of H3O plus is 9.7. So concentration of H3O plus is 10 raised to the minus 9.7. So if we do it, we get the concentration of H3O plus is roughly 2 times 10 to the minus 10 molar. So this is the concentration of H3O plus. So if we consider 298 K, at 298 K, so pKw is 1 times 10 to the minus 14, right? We already know. So this is nothing but a concentration of H3O plus times concentration of OH minus. So now we can calculate the concentration of OH minus. So concentration of OH minus is Kw by concentration of H3O plus. So concentration of OH minus is now, value of Kw is 1 times 10 to the minus 14 and concentration of H3O plus is 2 times 10 to the minus 10. So we get concentration of OH minus is roughly 5 times 10 to the minus 5 molar. So this is the concentration of OH minus. Okay, now we have got this one. So now the concentration of OH minus and concentration of NH2 NH3 plus, they are equal, right? Since the concentration of NH2 NH3 plus is equal to your concentration of OH minus, so we can write this as 5 times 10 to the minus 5. So the Kb, so Kb is 5 times 10 to the minus 5 times 5 times 10 to the minus 5, and concentration of NH2 is also given. This is 0.001. So if we calculate this one, we get Kb is 2.5 times 10 to the minus 6. So this is the value of Kb. So we need to calculate pKb also. So pKb is minus log 10 base Kb. So we get minus log 10 base 2.5 times 10 raised to the minus 6. So if we do it, we get the value of pKb. So pKb value is 5.6. Okay. So this is the value of pKb, and this is the value of Kb of hydrogen. Okay. Next we discuss problem number 15. It says for a 0.05 molar ammonia solution with an ionization constant of 1.77 times 10 to the minus 5, determine the degree of ionization and the pH. Also calculate the ionization constant of ammonia's conjugate acid. This is new here. Okay, so we start with let C is the initial concentration of NH3 in moles per liter, and alpha is the degree of dissociation or ionization of NH3. So the reaction or the equation is NH3 plus H2O gives NH4 plus OH minus. So NH3 is in aqueous medium, so NH3 aqueous here, H2O liquid, this is aqueous, this is also aqueous. So initially we have C moles of NH3. So C, and then this is 0, NH4 plus is 0, OH minus is 0 at equilibrium. Very similar treatment we are doing here. So C times 1 minus alpha, alpha is the degree of ionization we already considered. So C times 1 minus alpha gives C alpha and C alpha. Okay. So K, the ionization constant K, ionization constant of ammonia K here, or since it's base we can consider Kb here. Kb is concentration of NH4 plus times concentration of OH minus by concentration of NH3. So we write C alpha times C alpha by C1 minus alpha. So we write Kb is C alpha square by 1 minus alpha. So we can write this one like before, C alpha square, when alpha is very very small compared to 1, then we write 1 minus alpha is 1. So we get alpha is square root of Kb by C. The value of Kb is given, so 1.77 times 10 to the minus 5, and value of C is also given 0.05. So if we substitute everything, we get 1.88 times 10 to the minus 2. So this is the value of alpha. So this is degree of ionization alpha is this one. Alpha is 1.88 times 10 to the minus 2. Then we need to calculate the pH. Okay, so pH. Okay, so concentration of OH minus is C times alpha. So C is C times alpha is 0.05 and alpha is 1.88 times 10 to the minus 2. So this is the value of C alpha, or concentration of OH minus. So if we calculate this one, we get 9.4 times 10 to the minus 4 molar, right? So at 298 K, again we know Kw is 1 times 10 to the minus 14 equals to concentration of H plus times concentration of OH minus. So concentration of H plus, or H3O plus also we can write, instead of H plus we can write H3O plus. So concentration of H3O plus is Kw by concentration of OH minus. So we know the value of Kw as well as concentration of OH minus. Now we substitute. So 1 times value of Kw is 1 times 10 to the minus 14, and concentration of OH minus is 9.4 times 10 to the minus 4. So if we do it, now we get concentration of H3O plus is 1.06 times 10 to the minus 11. Once we got the concentration of H3O plus, we can calculate pH. So therefore the pH of the solution of the ammonia solution is minus log 10 base concentration of H3O plus, so minus log 10 base 1.06 times 10 to the minus 11. If we calculate this one, we get 10.973. So this is the pH of the ammonia solution. The next part is also calculate the ionization constant of ammonia's conjugate acid. Okay, so for the conjugate for the acid base pair, okay, so we write Ka, the acid base pair, we know Ka times Kb gives Kw. So we know the value of Kb, so we can calculate K. K is the ionization constant of the conjugate acid. Okay, so Ka is Kw by Kb. So 1 times 10 to the minus 14. Again we are considering 298 K temperature, and value of Kb is 1.77 times 10 to the minus 5. So we get the value of 5.64 times 10 to the minus 10. So this Ka is the ionization constant of the conjugate acid. Next we move to problem number 16. It says for the reaction CH3CO minus plus H2O gives CH3COH plus OH minus, calculate the hydrolysis constant, the degree of hydrolysis, the pH of 0.01 molar acetic acid solution, and dissociation constant of CH3COH at room temperature is given. So, okay. So part A. Okay. So if we consider hydrolysis constant for weak acid here. Okay, so the CH3COH is the weak acid, so hydrolysis constant of weak acid for a weak acid. For weak acid, we know the relationship, right? This is Kh, hydrolysis Kh is Kw by Ka. Now at room temperature, value of Kw we know 1 times 10 to the minus 14, and the value of Ka is given, okay, dissociation constant of acetic acid, so 1.8 times 10 to the minus 5. So this gives 5.56 times 10 to the minus 10. So this is the hydrolysis constant of for weak acid. Next, the degree of hydrolysis. Okay, so the degree of hydrolysis we already discussed these things. So degree of hydrolysis, if we say H is the degree of hydrolysis. H is root over Kw by Ka times C. So value of Kw we know 1 times 10 to the minus 14. Value of Ka is also given 1.8 times 10 to the minus 5, and concentration of acetic acid is given 0.1 molar, so 0.1. So if we all substitute here, we get 7.42 times 10 to the minus 5. Now part C, you need to calculate pH. Okay, so pH is half pKw plus half pKa plus half log C. So now you substitute everything. So pH is half pKw, value of pKw is 14, and half times value of pKa is also known, 1.8 also given, 1.8 times 10 to the minus 5. This is value of Ka, okay, not pKa. So Ka is given. So from Ka, so we take log minus log 10 base 1.8 times 10 to the minus 5. Okay, so this is the value of pKa plus half log C. Log C, value of C is 0.1, so 0.1. So if we all substitute here, so we get the value of pH is, first one is will give 7, the second one will give you 2.372, and third one will give you minus 0.5. Okay, so you get basically pH is 8.87. So this is the pH of this acetate solution. Next, problem number 17, given that the ionization constant of chloroacetic acid is 1.35 times 10 to the minus 3, determine the pH of 0.1 molar solution of acetic acid and 0.1 molar solution of its sodium salt. Now the pH of acid solution, so ionization constant is given for chloroacetic acid. Okay, so the ionization constant of given the ionization constant of chloroacetic acid, if we say this is Ka is 1.35 times 10 to the minus 3, right. So therefore, the concentration of H plus will be root over Ka times C. So we get root over 1.35 times 10 to the minus 3, and the value of C is 0.1. So we get 1.16 times 10 to the minus 2. Okay, fine. Now we need to calculate pH. So pH is minus log 10 base concentration of H plus. So minus log 10 base 1.16 times 10 to the minus 2. If we substitute all these things, we get the value of pH is 1.936. Next, we need to calculate the pH of the sodium salt of concentration 0.1 molar solution. So this is the first part. Second part, okay. So concentration of sodium salt, concentration of sodium salt of chloroacetic acid again, this is 0.1 molar, right. So sodium salt of chloroacetic acid is a salt of strong base NaOH, right, strong base NaOH and weak acid chloroacetic acid. So we know the formula. So pH is half times pKa plus pKw plus log C. Now Ka is 1.35. Ka means corresponding acid we need to consider. So Ka of chloroacetic acid is 1.35 times 10 to the minus 3. So pKa is minus log 10 base 1.35 times 10 to the minus 3. So you get pKa is 2.87. And pKw we know, pKw is 14 at room temperature at 298 K temperature. Okay. And C is 0.1 molar. So we substitute these values to calculate the pH of sodium salt of chloroacetic acid. So if we substitute those things here, so we get pH is half, value of pKa is 2.87 plus 14, and then we get log 0.1. This is 10 base again. So we get pH is 7.94. So this is the pH of the sodium salt of chloroacetic acid having concentration 0.1 mole. Move to problem number 18. It says calculate the solubility of A2X3 in pure water, assuming that either type of ion reacts with water. The solubility product of A2X3 is Ksp is 1.1 times 10 to the minus 3. So the solubility equilibrium is A2X3 gives 2A3 plus plus 3X2 minus, right. Now let the solubility be, so S such that concentration of A3 plus is 2S, right, and concentration of X2 minus is 3S. So Ksp, so since this is solid, right, and these are in aqueous solutions, so Ksp will be your concentration of A3 plus raised to the 2 times concentration of X2 minus raised to the 3. So 2S square times 3S cube. So we get 108 S to the 5. And given Ksp is 1.1 times 10 to the minus 23. So if we now calculate S, so S will be your, or S5 first we calculate, S5 is 1.1 times 10 to the minus 23 by 108, and from there we calculate S. S is 1 times 10 to the minus 5 moles liter inverse. So next we discuss determine the solubility of FeOH3 given that its solubility product Ksp is 1 times 10 to the minus 38. Also calculate the solubility in grams per liter and the molar concentrations of the ions in the solution. So for FeOH whole thrice ferric hydroxide, so we write FeOH3 in solid is in equilibrium with Fe3 plus aqueous plus 3 OH minus, right. So, if S is the solubility, then concentration of Fe3 plus is S and concentration of OH minus is 3S, right. So, Ksp, therefore, Ksp of FeOH whole thrice is concentration of Fe3 plus times concentration of OH minus raised to the 3. So, we get S times 3S raised to the 3, right. So, we know Ksp value is given here. So, it is 1.0 times 10 to the minus 38. So, gives 3 S to the not 3, 27 S to the 4. So, from there we can calculate S. So, S to the 4 is 1 times 10 to the minus 38 by 27. So, we can now calculate value of S. Solubility. Solubility is 1.39 times 10 to the minus 10 moles per liter. So, this is the solubility in moles per liter, but we need to calculate in grams per liter. So, in order to convert moles to gram, we need to use the molar mass of FeOH whole thrice, right. So, solubility in grams per liter equals to your 1.39 times 10 to the minus 10 times molar mass. So, 1.39 times 10 to the minus 10 and the molar mass is 106.5. So, if we calculate this one, we get 1.48 times 10 to the minus 8 grams liter inverse. Now, concentration of Fe3 plus is S. So, we get 1.39 times 10 to the minus 10 moles per liter, and concentration of OH minus is 3 times, right, 3 times S. So, S is 1.39 times 10 to the minus 10 moles per liter. So, we get 4.17 times 10 to the minus 10 moles per liter. Next, we move to problem number 20. It says find the minimum volume of water needed to dissolve 1 gram of calcium sulfate at 298 K, given that its solubility product is Ksp is 9.1 times 10 to the minus 6. So, first we let us consider the solubility of calcium sulfate. Let us consider the solubility of calcium sulfate CaSO4 is S, right. Now, the equilibrium is CaSO4 solid is Ca2 plus aqueous plus SO4 2 minus aqueous. Okay. So, since the solubility of CaSO4 is S, so concentration of Ca2 plus is S and concentration of SO4 2 minus is also S, right. So, Ksp is concentration of Ca2 plus times concentration of COSO4 2 minus. So S times S gives you S raised to the 2, and value of Ksp is given. So this is 9.1 times 10 to the minus 6 is S square. So value of S is square root of 9.1 times 10 to the minus 6. So value we get 3.016 times 10 to the minus 3 moles per liter. Okay, moles and liter inverse. So we need to calculate, find the minimum volume of water needed to dissolve 1 gram. So this is the solubility of CaSO4. Okay, so it's in moles per liter unit. Okay, now 1 mole of CaSO4. So we need to calculate the molar mass. So 1 mole of CaSO4 is calcium is 40, sulfur 32, and oxygen is 16 times 4. So we get 136 gram. Okay, so this many. So if we multiply this with 136, we get the grams of CaSO4 dissolved can be dissolved in 1 liter. Okay, the solubility is now of CaSO4 is 3.016 times 10 to the minus 3 times 136. This is grams per liter, right? So if we multiply this one, we get 0.410 gram. Okay, so it says that therefore 0.410 gram is dissolved in 1 liter. Therefore 1 gram can be dissolved by 1 by 0.41 liter. So 2.44 liter.